Welcome to Pastor Victor's Academy. Embark on a journey through the world of engineering mathematics and electrical engineering with our educational tutorials designed specifically for engineering students. Whether you're mastering calculus, solving complex circuit problems, or exploring power systems, Pastor Victor's Academy is your ultimate learning companion. Join us as we break down complex concepts into clear, easy-to-understand lessons, helping you build the foundational knowledge and skills needed to excel in engineering mathematics and electrical engineering courses. Subscribe now to kickstart your learning journey and gain the confidence to tackle engineering challenges head-on. Let's unlock the world of mathematics and electrical engineering together, one lesson at a time.
In this video, we'll be looking at the vaporization processes of pure substances. So please do want to pay attention as we go on. You'll be learning a lot in this video. So we want to look at PV process. And we'll have the system, then we'll have Vx, Vy as initial volume. Then we'll have 3 atm, 2 atm, 1 atm. Here we'll have 100 degrees centigrade or Celsius, 120 degrees Celsius. Then look at what happens when temperature is fixed at 100 degrees Celsius. Because what we do in PV process is that temperature is kept constant instead of pressure. So first of all, fix the temperature. We keep it constant throughout the process. So we are working with a temperature of 100 degrees Celsius. Then initially the pressure was at 3 atm and we can see the volume. So trace it down, it tallies with Vx. So what do we do to get to boiling point? We said when pressure is high, boiling point will be high. What that means is that for a higher temperature, pressure needs to be what? Higher. For a lower temperature, pressure needs to be lower for us to get to what? Boiling point. So we started with pressure that is higher than the boiling point pressure. Then we started reducing. So you can see that the graph here has a negative slope, whereas the graph of the TV process has a positive slope. While we are reducing pressure, pressure is varying inversely with volume. So as pressure is increasing, volume is reducing. As pressure is reducing, volume is increasing. So that's what we have here. As the pressure is going down, what happens to the volume? Volume is changing. Now, at 1 atm, the liquid reaches boiling point. That's the water reaches what? Boiling point. So from here, the pressure of the system no longer does what? Reduces. It remains constant. Likewise, the temperature, which is already constant. The more we are trying to reduce pressure, the more the liquid is changing to gas. And that gas will create pressure, cancelling the effect of the pressure change we are trying to introduce. So the pressure would remain constant and the volume keeps increasing until we get to the saturated vapor curve. So at the saturated vapor curve, all the liquid in the system has changed to what? Vapor. So from this point, pressure is no longer what? Constant. So it keeps reducing, and as that is happening, the volume of the liquid is what? Is increasing. So remember this ratio. The ratio at which volume of vapor changes compared to volume of liquid with changes in pressure is what? Is higher. That's 5,000 times that of compressed liquid. So that's why we have this kind of slope on the vapor region. Now, what happens when we work with a temperature of 120 degrees Celsius? Now, we start with the same 3 atm. Starting from there, so you notice that this is a higher temperature compared to what? Compared to this. So when pressure is fixed, higher temperature would give birth to greater what? Volume. That's why our Vy becomes our initial volume instead of Vx. Why? We are working with the same 3 atm at a higher temperature, so we would have a higher volume. So our liquid has a volume of Vy. Then we keep reducing pressure. As we are reducing pressure, when we get to 2 atm, water starts boiling. We can no longer reduce pressure. Pressure becomes constant and temperature is already constant. So the liquid begins to change to vapor. That keeps happening until we get to this point as the saturated vapor where all the liquid has changed to what? Vapor. Then pressure can now continue reducing at that constant temperature. And as that is happening, the volume of the vapor keeps what? Increasing. Now you can see that the graph with higher temperature has lesser steepness on the vapor, the superheated vapor region, compared to the one with what? Lower temperature. Because here, since we have higher temperature, when we enter the vapor region, molecules will be more energetic. So reducing pressure will cause a greater change in volume compared to this. That's why this is less steep, indicating that there is a greater change in volume here. Whereas this one is more steep, indicating that there is a lesser change in volume here. So don't assume that we can reduce pressure to zero, because where we have zero pressure becomes a vacuum. That means there is nothing inside it. So for us to have water inside the system, that means the pressure cannot be reduced to what? Zero. So what happens at the critical state for the TV process is what happens at the critical state for the PV process. Within the dome, we are having a horizontal line for both graphs. The reason being that both pressure and temperature become constant within the dome. That's that point of what? Saturation. So until the whole liquid changes to vapor, the pressure can neither increase or decrease. Likewise, the temperature. It is after the whole liquid has changed to vapor, that is when temperature can now increase or pressure can now what? Decrease. I want to explain this issue of steepness on the vapor region using the ideal gas equation, because the moment water gets to the superheated region, it behaves like an ideal gas. So remember that the ideal gas equation says PV is equal to KT. In that case, for temperature specific volume graph, dt dV is equal to P over K. That's when you differentiate temperature with respect to volume, you will get P over K. This is a sketch of the PV graph. And remember that this one would have a higher pressure compared to this, and pressure is constant throughout. So what this means is that the slope is constant. That's both P and K, because K is a constant. Now we are making pressure constant throughout the process. So P is also a constant. So the T dV is constant. But what's the difference between the slope of this and the slope of this? Since this one has a higher pressure, the T dV for this will be higher on the vapor region. So you can see that the slope is greater. That's why it's steeper than this. Now, when pressure is lower, the slope will be lower. So that's why this one has a lower slope. So what that means is that the higher the pressure, the higher the slope. On the vapor region, it becomes steeper as the pressure is increased. But for PV graph, what do we have? dP dV is equal to minus KT over V squared. So the fact that we still have V here indicates that the slope is not a straight line. That is not constant. It is changing. So that suggests that on the vapor region, we are not supposed to have a straight line. Instead, we are supposed to have a curve that flattens as we approach what? Infinity. So that's what we have here, a curve rather than a straight line. Now, if we are working with the same specific volume for these two, let's know what the difference in their slope would be. So when volume is the same, our concern will now shift to temperature, because this is already a constant. So the greater the temperature, the more negative the slope. In other words, the slope becomes smaller. So that's what we have here. This one has a lesser slope, but negative compared to this. This one has what? A greater slope, which is still what? Negative. So when you look at these two things, it is just like flipping the graph. That's flipping these two graphs. When you flip, you will notice that the one that has a greater slope is now the one up, and the one that has a lesser slope is now the one what? Below. So that's how this formula explains the difference in slope on the vapor region. That's what you need to know about the TV process and the PV process. They are called vaporization processes of pure substances. So thank you for watching. I really appreciate. Please do well to like, share, and subscribe. Help me share. I want to reach more students. And don't forget to subscribe. Once again, thank you for watching. God bless you.